Et donc, Christophe est arrivé, donc nous pouvons commencer. Good afternoon, everyone. I will have the pleasure to chair this conference. I need first to introduce our guest speaker tonight, Federico Capasso. Federico studied physics in Italy, as his name lets us guess. But then very soon he moved to the States and to Bell Labs. And basically in Bell Labs he has been raising the ladder from member of the staff to blah 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 to head of the lab and to vice president for research. And then he was too close to the top at Bell Labs. He decided that he should move to Harvard, where he is now. And well, I mean, I known Federico before bumping into Federico at Bell Labs. I known him for the concept of bandgap engineering, which was a very interesting concept. Basically, with semiconductors, you just invent the structure you want to do and you do it. And not only the concept was proposed by Federico, but he devised a very interesting structure, which is a quantum cascade laser. I mean, I think it's his favorite, where the design of the structure is a major piece of art. I mean, really, and the fact that the thing works always amazed me. But then since he has left Bell Labs, he's been working on other things. I've been reading that you're working on quantum photonic crystal cells. So QPCT cells, something like that?
No, not those, not that thing yet.
Not yet. And also on Casimir forces and everything. I could take the list of the awards that Federico has been awarded, but then we would be missing the talk. So I suggest that we directly move to the talk, and let me tell you to welcome our speaker tonight.
Thank you very much. This must be my fourth time here to give talks, and it's always good. And I have a string of undergraduates from the Ecole Polytechnique that come every year to my lab, and I would say it's been now a total of probably more than 15. And they all do very well. And so this is the subject of my talk. I sort of started to work in this area. I got interested in metamaterials. You know, metamaterial is a very hot topic these days. People are talking about perfect lens, cloaking, and so forth. But being the fact I've always been interested in working at the interface between science and technology, I didn't see a lot of opportunity in 3D metamaterial for technology. After all, you know, if certain concepts are around, and I'm a bit polemic in saying it, and intentionally so, a concept like cloaking around for now more than 50 years, and nothing happens of any technological significance, you have to ask why. And it's very simple. These materials are very hard to make. Making a three-dimensional optical material is hard, right? No wonder that electronics is a planar technology. No one talks seriously about doing three-dimensional type of electronics. So I started to think about, can we do engineer optical material on the surface? And I didn't invent the word metasurfaces, by the way. Some, you know, like to attach labels to it. And so I'm going to talk about metasurfaces. And this is kind of an ensemble of things that we have been doing. So let me get started by first saying the people without these, I probably would just be writing some proposal and have some ideas, but that's it. They make it all work, and some very talented postdoc, Reza, who now moved to Magic Leap, who is one of the hottest startup companies. In fact, they are working in this area as well. Okay, Rob Devlin is a very talented graduate student who invented the atomic layer deposition process that made a lot of, for titanium oxide, a lot of these things. Charles from the Ecole Polytechnique, I was hoping to get him as a graduate student, but he went to MIT, which is fine. MIT is also a great place. Okay, and then others people, undergraduates, and also collaboration with Professor David Clark. So these are some of the funding. Was very inspiring to work to interact with Google. They didn't give me a lot of money, but they gave me some good problems, and I'm always grateful to them, and also Thorlabs. So let me start. It's very simple. How we started to think about is through Huygens Principle. In fact, it's so simple that it borderlines trivial. I'm sorry, but that's how we got started. So assume that you have an interface, okay, and we know that we construct the wavefront as we move from one material to the next by taking the envelope of these wavelets. Now, suppose now that I engineer an interface between two media or a surface with sub-wavelength space elements. These can be like antennas, any kind of things you think about that scatters light, a light scatterer. And I can design them point by point, their sub-wavelength space. So now how these wavelengths, if you like, the size, how these wavelengths are shaped, depends on the local structure of these phase shifters. The most important part here, even though we engineer the amplitude, the polarization, is the engineering of the phase. So point by point, you can think of it. These are sub-wavelength structures, also very thin, that there is a phase shift locally. So you have a phase map, and the phase map will determine the actual wavefront that you create. And you can think in terms of Huygens again. You take the envelope and so forth. And so that was how we intuitively started to think about it. Of course, we do a lot of simulation at the end. It's all rigorous. Whenever we can, we do analytical model. And essentially what you can do is make a whole class of flat or nearly flat planar optical components that you simply digitize. This you can call digital optics, okay? I will explain the difference and commonality with Fresnel optics. This is just a couple of slides. So I'll tell you what a bit is my vision, okay? And in fact, you know what I want to do? I should be moving here because otherwise my neck is going to get too stiff here. Okay, okay, this is perfect. Okay, so our goals is to create a CMOS-compatible flat optics platform based on this material, titanium dioxide, where we see there are some high-volume markets. Okay, titanium dioxide is a commonly available material for the visible, of course, for the near-infrared we can use it. And we'll try to convince you that the process we have come up actually can be moved to the chip makers that make integrated circuits. So, for example, if you take your cell phone here, okay, this is a camera module. There is a chip sensor, which is silicon, and then there are 6 lenses. The lenses are made by totally different technology, which is called molding. It's a 19th century process. Yes, it's been perfected, of course. And so our point is that we see a future where one can use the same technology to make not only the chip, but also the actual stack of lenses. Ultimately, yes, I think there is a hope to really have a game-changing type of technology. And then, but I'm going to want to go back of the underlying physics. All is based on maybe essentially digitizing the surface by zeros and actually one, pillar, no pillar, and so forth. Or whatever phase shift you want to do so that you can control locally the phase, the amplitude, and the polarization of light. So it's really creating a library of phase shifter. And then this is the key point. With a single phase mask, single lithographic level, you can generate a meta-optical component. As I will show you, it gets more interesting. You can design a phase mask such that you can create multiple functions on the actual same chip. Even though the emphasis maybe is a bit more on the technology, I will also show you some very interesting application more on the physics, because once you can engineer, arbitrate the wavefront, you can do kind of very cool stuff. Okay, so, and well, this is the parallel. In fact, when I started to interact with actually Google, I was lucky to interact with the head then of the Google Glass project, Bernard Kress, who is a Frenchman, in fact. And he told me, yeah, Federico, the reason we are interested in moving from this, that of course, you know, he basically said, you know, single digital pair, one mass level, you can create an arbitrary analog phase profile. There are other advantages also. You can control the dispersion, and it's far easier to get achromatic behavior and so forth. But basically, yes, we are doing diffractive optics in ways that I think will open up a lot of opportunity, certainly for technology and probably also for asking some very interesting scientific questions. I will give you some example, in fact, near the end of the talk. So it's all about engineering the phase, this phase shifter. So this is our first paper in this area where we engineered the metasurface with these V antennas here. And we started with metals, but then we wanted to go to the visible. Metals are no good for the visible. They're in fact no good for the near IR. So we moved to dielectric structures and so forth. And just in case, these are two review articles. In fact, I was fortunate to have with me for 5 years Patrice Genevet from University of Nice, who is, after a long detour for 5 years in my group, went to Singapore, came back, is now director of research at CNRS in Sofia and Antipolis. So these are two reviews. The first thing we asked, you know, can I design a metasurface such if I come with a certain angle, with a plane wave, I scatter and create a plane wave, and the plane wave can come out at any angle that you want, either refracted or reflected. So we use simple Fermat's principle to understand. You see, I'm quoting a lot of new and old French scientists here in my talk. This is not done on purpose, of course. It's just that France did so many great contributions in optics. So basically, it's very simple type of exercise. We say, suppose that we can engineer a sub-wavelength space metasurface here. And we make the ansatz that the phase gradient is actually constant here. Then you can write, if I come in with an angle of incident theta I, you can ask what is the angle of refraction, and let's call it of anomalous reflection. So you can see, you can call these are kind of generalized Snell law and reflection law. And the key point now that this gradient acts like an effective wave vector. You see, so since these laws can be understood as a conservation of lateral wave vector during, as you go through, as you interact with the actual surface, this is a nice, simple way to think about it. The good thing, you can engineer any way you want this phase gradient, as long as it is constant, so you can engineer these angles here. So, and that created a lot of interest. This is our first paper. So we demonstrated this in the mid-infrared using, this is a unit cell. These are these V antennas. The V antennas are designed to create a constant phase gradient so that I have a phase coverage from 0 to 2 pi, which I need to have in order to have a wavefront, basically. So we took data. And for example, this is a normal incident. There's always some light going through, if you like. There is a filling factor and so forth. And this shows the anomalous refraction angle. You can get sort of quote-unquote negative refraction, although this has nothing to do with the negative refractive index like in 3D material. Now you can ask, you see, this is obviously what happens to this order. The order with the opposite sign is actually cancelled out by design. By design, using that recipe, you simply annihilate if you call this a -1 order, you destroy the actually +1 order. The next thing we said, can we make an entirely flat lens? Okay, we know why lenses are actually bulky. Again, ideally in an actual lens, you want to have that all the phase shift, they are the same, so you converge to a diffraction limited spot. But in reality, this is not possible with this shape because of Snell's law, in fact, you have spherical aberration. So if you make a completely flat lens and you use this hyperbolic phase profile, the physical argument is exceedingly simple to understand, okay? Essentially, this is flat, so you go from here to here. You have a different propagation phase shift than if you go from here to here. So in order to make sure that the total phase shifting going from one point to the other, you have to introduce locally an antenna that produces a phase shift that compensates for the phase difference. You see, it's all in here. This is a phase shift that you introduce locally, compensates for the phase difference between these paths here, the generic path starting from X and Y with respect to the central ray. So simple argument. So we were able to show diffraction limited focusing, very close analogy with simulation. Of course, it is a completely useless lens for a variety of reasons. I mean, the efficiency was very small, but it was an existence proof that and this has created a lot of interest also from an industrial point of view. But of course, we wanted to make something potentially useful. So we said we have to go to the visible and move then to dielectric structures. Okay, and by the way, if you move to the electric structure, you can use kind of pillars. Now again, here you can come up with a very simple physical picture. A pillar introduces a phase shift, right? And the phase shift depends on the effective index. You can think of this as a sub-wavelength long waveguide, right? So by controlling the diameter, you vary the effective index of this mode, so you can control the phase shift any way you actually want. And again, what is it? This you can see, you can call, certainly is an example of digital optics, one mask level, and I can show you how you can correct for aberrations and so forth. And so this is the process that my student Rob Devlin came up with, and it's actually very nice, okay? We use e-beam lithography only because we are a university laboratory, but we have talked to a lot of companies. This process is entirely transferable to other lithography, such as the lithographies using steppers, or possibly also nano imprint. We are looking at this. So you start with e-beam resist here, you define an actual pattern here, then you grow a titanium oxide film by atomic layer deposition. This is the conformal process, very low roughness. And I will give you some more detail until you fill up, and you fill up here, and you grow until you have filled up the biggest feature here. So if the biggest feature here is W, then you grow a film up to W half. Then there is a chlorine etch, and after that, further processing, you come up with a complementary structure. So the question is how good this is. And it's actually quite impressive. This process, even though it was done in a university lab, is highly reproducible. I mean, basically, the only time things go wrong if someone forgets to refill the actual chemical in the middle of the run, everything stops and is messed up. But other than that, you can see these are different metasurfaces. These are completely vertical walls. This one accidentally fell over. And how is this done? Okay. This is amorphous titanium dioxide. It has to be grown at very low temperature, 90 degrees, to have low roughness. If you exceed around 100, 120, then you start get the crystallines, and that spoils the roughness and so forth. At a higher temperature, you can grow the crystalline phase, which is called the Anatase phase. So we stay intentionally at low temperature, these are.
What's the aspect ratio?
Oh, we've gotten up to 20. This is about 10 to 1. We have done experiments, I think my student up to 15 to 1, maybe 20 to 1. Okay. It's highly repeatable. I mean, it's a vector, and this is essential for phase control. In fact, I'll show a picture in a few moments. So these are thin films, you know, the measurement, ellipsometric measurement of the N and K. There is no loss in the anterior visible. The good thing, you get pretty high refractive index, which means if you can really have a good filling factor okay, because you can have good confinement. And now, I don't want to spend time, but they started to ask me so many questions. Well, it is a slow process. I don't want to spend 5 minutes in this, but this argument makes it clear because you can process so many wafers, and then if you go through the rate of a titanium oxide deposition and so forth, you can turn out 70,000 chips per hour with a standard ALD machine. So this is a problem of absolutely no concern, the fact, because essentially you're doing parallel processing of actually many, many wafers. And these actually, we worked out the details because I said I'm getting a bit tired of asking this question, but I shouldn't get tired. I should give a good answer, and I think this is a good answer why it is not an issue for the technology. I want to give credit to early work. The group of Philippe Lalande in the 90s, in fact, did some very interesting work with titanium oxide. They were using a different technology. They were etching with reactive ion etching. They were not using ALD. So you see, they were not good vertical walls. This is a very significant problem because even a 4 degrees tapering can produce a very significant phase error. So what they really were only able to demonstrate is some pretty good blaze grating at these wavelengths here, but already their lens was very problematic, so there wasn't any follow-up of this work. And I'm not saying it can't be done this way, because you never should say that, but I would say it's highly improbable that this process can be improved in terms of technologically to make some good devices. So this is our paper last year. We made essentially a meta lens. This was a monochromatic lens designed for selected wavelengths, blue, red, and green. And we showed high numerical aperture. This is important. We want to show we can do something as good as a commercial objective. These are infinity corrected, meaning light comes normally on your thing from infinity. And we are looking at the focusing properties at these different wavelengths. So we use different sizes. We went as large as 2 millimeter, but with our process we can go, I think I've killed the laser pointer, no. No, it's alive. We can go up to 3 millimeter. So we went high numerical aperture. We wanted to show really sub-wavelengths focusing. Now, I'm going to discuss this way of constructing the phase. This is the famous Berry-Pancharatman phase. Basically, that phase profile you can simply arrange by, these are they are half-wave shifters, okay? So they shift the phase by 180 degrees. And you can show, using Jones' formalism, that essentially, by varying the orientation here, you can actually produce a phase locally which is related, which is basically twice the orientation angle. I will explain that in detail later for another device. So the advantage, of course, it's polarization sensitive, it could be useful, that you can make all the fins the same, you just change the orientation angle depending on the position, so you can create that hyperbolic phase function that allows you to get diffraction limited focusing. So this is actually how, you know, these are phase shifter half-wave plates. So we use essentially shaped by refringence so that there is 180 degrees phase delay between the X and Y components of the field here. And so this is at the center of this Berry phase design, but again, I will cover it later. These are the data we compared. We were able to show basically diffraction limited focusing for 3 different wavelengths. At these wavelengths, we compare them to a state-of-the-art objective. Now, it's not fair to say that we are doing better. The way it looks better is because this objective is also corrected for all the other aberrations. So they are trade-off. But it's still a good existing proof that we can do this. And with a high numerical aperture, In fact, this got the interest of Zeiss. The Zeiss people, we have a collaboration now. They've been in my laboratory for a week. They've been reanalyzing all our lenses. I'm happy to say they've confirmed all our results. It's good to be validated by the leaders in the field. And hopefully this will continue. So we did also imaging. These are standard targets. This is called the Air Force target. So you illuminate it with a blue source, a green source, and so forth. And then you image with lenses that are optimized at these wavelengths. This is a Siemens target. This just says basically you can easily see, micron-size feature, well-defined, of course. But the question is, can you do actually sub-wavelength imaging? So now if we made this target by focused ion beams, so these are holes which are basically hundreds of nanometers hole, so you should be able to image them do sub-wavelength images, and this shows it. Now, of course, you can see that there is also some coma, right? There is little tails here. The reason this coma, this is an extended object, so some of the rays are coming at a certain angle, so we have to correct for coma. And we have done this, in fact, very recently. I'll show you how you can correct coma. Okay? So now, of course, you have to show also you can make polarization in sensitive planar lenses, and so you use pillars, same recipe as before. Well, you can see from this that this indeed is an actual diffractive lens, no question about it. Okay? So the period here, this zone becomes shorter and shorter, so you have a 2 pi phase coverage from 0 to here over a shorter distance because you have to deflect these beams on the edge of the lens more than the ones here. That's sort of a simple way to understand this. The quality of the pillars is still very good. We measured also, these have good focusing efficiency. We made no attempt, by the way, to maximize the focusing efficiency. You can do interesting optical impedance matching. In fact, this interesting problem to essentially, ideally, we should be able to get essentially almost completely cancel out any backscattering or any reflection, but we haven't done yet, but at least it's theoretically possible. And it's important. So we also showed here diffraction limited focusing. Again, these are three separate lenses at three different colors. This is recently we addressed the problem of coma. Okay, coma basically is the following: that again, if you come in a certain angle, the focus gets basically messed up. In fact, if you take the hyperbolic metal lens that I showed you before, and you actually come with rays at a given angle here. This, we use a commercial ray tracing tool called Zemax, which is widely used. You can see this Zemax plot of the ray tracing. You see, as you change the angle of incidence, you get this chromatic type of aberration. If you are normal, you get a diffraction limited spot. Okay, if you come at an angle, it gets messed up. So now you can, however, correct it by doing the equivalent of a doublet, but a different doublet. And here, again, using some intuition is kind of interesting. So the way we did this is actually by in one metal lens here, the one here to modify a bit the hyperbolic phase profile for a way, particularly here, you see there is quite a deviation. And here there is this interesting thing. Now, those of you that know how you correct aberrations for telescopes, or has been corrected, I don't know now, but certainly for a while, they have these Schmidt plates. This acts as a Schmidt plate. You see this other part here. We can call it an aperture metal lens, where here you have a converging effect, and here you have a diverging type of a effect. Okay, so those side rays that want to be bent more, now you bring them back to what is supposed to be your focal point to achieve. So this is in fact shows how the ray tracing work again. The singlet meta lens is aberrated with coma here. If you take the other lens, the focusing meta lens, this is the one that is not exactly the hyperbola because it is a bit modified. So it's modified in a natural way that it's aberrated clearly. This is not clearly diffraction limited focusing. It would be a joke to say so. But it's aberrated the same, basically, very similar for different angles. Now, if you add now the aperture meta lens, what I call the equivalent of a Schmidt plate, you see you're now bringing back these here to here, and now you get the same focal distance. Basically, you get diffraction limited focusing for a certain field of view. And by design, you have to design field of view. So we took a significant field of view. For example, this is a field of view of 50 degrees, plus 25 and minus 25 degrees. And we showed basically that you get a focal spot essentially identical for this angle. This is important because coma is an important thing to actually correct. And so we are quite happy with these preliminary results, and we are spending a lot of work to correct for aberration. Now, this is a very interesting thing. This actually problem was formulated to me by the Bernard Kress, who was at Google then. And we wanted to make then a fully achromatic lens. And he said, Federico, don't waste your time on that now. We are interested for AR, VR. We are interested first in a collimator, a device that can diffract light at 3 different wavelengths by exactly the same angle. Can you do that? And we actually did it. And then can you make a lens that focuses only 3 wavelengths, ideally blue, red, and green? At that time, we didn't have the titanium oxide technology, so we did it with the actual near-infrared. So the actual physical argument here is actually very simple. Again, you know, it all goes back to Young and Fresnel. I tell my students, even the most complex thing you can reduce sometimes to the simple experiment of optics. Like here, you know, you just take the phase difference of these paths. And so in this case, you see, we have to make sure that 3 wavelengths are diffracted at exactly the same angle here. Okay, so what you have to do here is to make sure that these phase shift, okay, at the same, essentially, the propagation phase, you see, depends on the wavelengths, obviously, right? So what you have, in order to have this collimation at the same angle for 3 wavelengths, you have to locally construct a resonator using the resonances of a resonator. So let's say 3 wavelengths, you introduce phase shifts that compensates for the difference in propagation phase for these 3 wavelengths. So if you do that, it comes out, we were able to do this. This is in this paper here. And then, of course, it was not enough. They wanted us to do a lens, and that's a bit more difficult. So this is actually not, it focuses into a natural line, not a spot, because it was just simpler to do then and so forth. And so you see, these are the data points here. We were able to, it was okay, it was a good start. We were able to get the same focal lengths at exactly these wavelengths, but they wanted it to fall off the cliff rapidly on both sides. Rapidly means within a light-emitting diode bandwidth, which we couldn't do that. We know how to do it. In fact, we have done it in the visible now, but I'm not quite ready to show the data yet because we have to analyze them. Okay, so now we have made a meta lens that focuses 3 different red, blue, and green within, and it falls off very rapidly around the actual design wavelength. But that's basically, so the underlying physics, so these are the data, in fact. So you see this structure actually at design. It's a bit of a complex structure here. Essentially, this introduces a different resonant mode in such a way that at the end of the day, you get the same focal length as you see here, 7.5 millimeter for different wavelengths. Okay, so this is a good start. The next what we did, and this is a complex subject, and in order to do justice to it, I would have to spend quite a bit of time, in probably 15-20 minutes, so I'm just going to give you a really bird's eye view. The interesting thing of this way of doing of diffractive optics, you see, we all know that in diffractive optics there is a say, the focal length must be decreasing with increasing wavelengths. But we actually show that by design you can do an interesting design in such a way that you can have the opposite dependence on wavelengths. So we published a theoretical paper on this. So there are a lot of possibilities of these meta-optics. This is a first step we designed. This is a lens in reflection that focus in reflection because you get twice the phase shift, and that can be useful. So again, and we used here, this is polarization insensitive, Y squares because you have maximum filling factor. So we were able, by essentially doing dispersion engineering here to do the following, to create a lens which had the same focal length over a light-emitting diode bandwidth. Now, recently, and I'm telling you, this is 3 days ago, basically, my people have shown me, one of my top postdocs, data. They've been able to make actually a broadband lens from the red, blue, green, and blue with basically the same focal length with better than 5%. The efficiency is not very high, but it's a good start that you can do. I think so. It's only a matter of time. Hopefully, we will be able to demonstrate a broadband lens with even higher efficiency because that opens up. Again, this is now only for infinity corrected. So on that, we would have to add comma correction. But we understand more and more how aberrations work. And again, this is now going back to the 60 nanometer bandwidth lens. We were able to show diffraction limited focusing, which is nice. Now I want to go to the multifunctionality. I hope I will convince you that you can design phase functions in such a way that you can do interesting things that if you did with normal component, you would have lots of components. So I call these multifunctional metasurfaces. For example, we have made also, I'll show you this, we have made a metaspectrometer, okay, that essentially the idea is to have the same resolution of a 1 meter long spectrometer, but much shorter propagation distance. And with these meta-optics, it's kind of conceptually easy to do. If you want to do chiral imaging is basically this. Some people call this dichroic spectroscopy. Essentially, there are certain objects like beetles and other that the reflectivity depends on the polarization of the incident light. Okay? So this can be called chiral imaging. So if you want to do chiral imaging with ordinary component, becomes quite elaborate. So we ask ourselves now, can we look at one of these nice objects, these beetles? You can buy them for a few dollars from Thor Labs, and you illuminate them, and you create you illuminate it, let's say, with red, blue, and green light, and then, depending on the incident polarization, the same lens can create the image for circularly polarized, left circularly polarized, or for right circularly polarized. So you can do essentially in a simple way with a single lens and a camera chiral imaging. So I haven't quite explained to you like the Berry phase works, but I will do that later. But essentially, you can design, you can put in a single lens a multiplex design of 2 lenses, one that focuses left circularly polarized light and the other right circularly polarized light. Okay, and this we did in this paper here. And so this is a detail. There are 2 designs meshed together, again with titanium oxide. This is a test. We use an output from a fiber. In fact, this was a supercontinuum laser. And of course, if you come out linearly polarized, you'll see 2 images here. Okay, if you come with left circularly polarized, you will see this image here, and right circularly polarized, you will see this image here. Okay. Now, if you hit a lens which is designed for right circularly polarized with left circularly polarized, happens essentially that the lens doesn't focus. It basically scatters. It is actually diverged. Okay, and we actually checked that. So you can get these nice images. In fact, we did some detailed spectroscopy on this. So it's a simple example, I think, where you can do in a much simpler way something than it's done with the traditional optical components such as plates. What I haven't done, because I didn't have the time, but in fact we are going to try to make a product out of it. You know a polarimeter, what a polarimeter is, right? A polarimeter essentially is a device, if you go to Toll Labs, a polarimeter is something that occupies things and it's a complete object. We made a polarimeter with just a single metasurface, okay, that essentially measure the Stokes parameters. Okay, so you can determine the full Stokes vector, including the actual depolarization using a single metasurface and an actual camera. And it's actually quite exciting application, but it would take too much time for, you know, in such a talk like this to describe the details. We have been thinking now, how can we make a highly dispersive, very short spectrometer if we can design a meta lens that works off-axis, and so that with a small change in wavelengths you get this large difference in actual focusing. Wow, then you can make something very interesting, you see. So this is our principle, to use an off-axis meta lens, okay, highly dispersive, so you can do over a short distance what a typical spectrometer does over actually large distance. So we made a first small step, but a relevant one. Essentially, we demonstrated the ability to get, you know, 0.05 nanometer resolution, a spectral range up to actually 200 nanometers. Now, of course, the challenge here, we need to increase the actual spectral range, but we should be able to do it. But again, just look at the size difference. So I think we've been in touch for this work with Toll Labs. We have started a sort of a nice collaboration. Alex Cable is the chair, CEO of Toll Labs. He's an old friend from Bell Labs. He worked for actually Steve Chu and did the famous experiment on optical molasses for which Steve Chu got the Nobel Prize in Physics. And Alex Cable. And Alex, in fact, started Toll Labs when he was at Bell Labs, kind of secretly. But actually, Steve Chu knew that he was so good, he would let him do it. You can start your own company as long as you do great science, help me do great science. So I reconnected after many years, and he's a... Now, this is now interesting. You know, I said it's not a dream. I think we are aiming pretty high. The goal is to replace a camera module with a lens. So how on earth can you make a tunable meta lens, right? Because, you know, the way it's done typically, tunable lenses is by translation of rigid optical components. This is, I'm sure many of you will recognize, this is a typical camera zoom systems, okay? So longitudinal motion in all cameras for zoom and focus, mechanically controlled, limited speed, and so forth. So, and then there is, of course, more specific type of applications here. And so this is unpublished work, but we are quite excited about it. We are writing it up, essentially a collaboration with David Clark's group. The idea is the following here. We need to have something that essentially we need to stretch the lens this way in such a way that you maintain diffraction limited focusing. And this is really brilliant work by one of my best students, Alan Shi, working with a second student, Shuyan Zhang. And essentially this is the following. Okay, you use an elastomer. An elastomer has, you build a meta lens on an elastomer with a process, the details are shown here. This is made actually of silicon on actual glass, this meta lens, because it's near infrared, is transferred on the elastomer. And then what the elastomer, like VHB or silicon, has a property, if you apply a field this way, it stretches very significantly this way. Now the challenge is what happens to the electrode. If you use any metal you can think of, it's going to break up, right? However, there is very interesting developments in actual carbon nanotubes. So my students use single-wall carbon nanotubes, a very high compact mesh that you can stretch. You don't need conductivity. You don't need conductivity. You just need voltage. Although they have reasonable conductivity, and this is a summary of their data. Basically, they are designed in such a way that you have a stretching of a focal length variation over up to 100%, and I saw the data, in fact, we are putting in the paper now. It remains diffraction limited, the focus, for normal collimation, of course. So I think this opens up a lot of future possibility for technology. Here I'm listing them and so forth. So now I want to move really to the more physics-y part of my talk. And there's quite exciting things that you can think of. So when you talk about metasurfaces, you can say, can metasurfaces help do something that, for example, axicons do? Axicons create Bessel beams. It's well known. Right? You can think in a very simple way here. An axicon, plane waves come off in a cone-like shape. They interfere constructively, and over this region where they interfere constructively, you have a pencil of light. You have a focused pencil of light. It is a diffractionless beam over this distance here. The way it's done is this way here. Now, then you can ask the question, this is typically, this was demonstrated many years ago. It has low numerical aperture, high efficiency. The problem here is total internal reflection. Now, you can do high numerical aperture but low efficiency by aperturing this high NA objective here. Now, and this way you can make the first Bessel beam. It's called J0, the first Bessel function. What if you want to do? So we asked the question, this is in this paper here. Can you make a metasurface that in principle can create any high order Bessel beam? Okay. And solve some of these problems here, have both high efficiency and high numerical aperture. These are the two questions. I want to go first. If you want to make the second Bessel beam, J1, you can call it a bottle beam. It's a diffractionless beam where at the center there is no light. It's like dark, right? How do you create it? Well, it's very simple. You add a vortex phase. So you have to add a vortex plate. You could think of simply a spiral, like the early days, or you use 4 holograms, whatever. But you need more than one component. So what we have shown here that you can design a metasurface in the following way. This phase essentially by itself gives you the J0 beam. But you can add a phase which is a vortex phase. And depending on actually n, you can create ideally any Bessel beam you actually want. So we made a blue, a green axicon, and also a red for J0 and J1. And the results actually are very nice. They are high efficiency, this stuff. It's in this, 70, 80%. This is for the blue, for example. The J0 beam, you see you have a diffractionless distance. With the camera, we go here, you see this. And here you have, shows you that you essentially get what you want. And this is another metasurface that creates a J1 beam. So there is a 0 intensity here, and you can see there is a diffractionless distance of the order of 100 micron. So there is a lot of potential to create structural light with metasurfaces, both in easier way, in a sense you need less components, and probably things that you cannot do by other methods, and I will try. So of course this is very exciting stuff, orbital angular momentum. If you have a helical, you can have beams that have essentially orbital angular momentum, and this is well known, and you add, if you like, a phase factor like this, and L represents the number of twists of the wavefront within a wavelength. That's defined the angular in a very famous paper in Physica Review A of by the Wardermans group in actually Netherlands, 1995. Not only they did all the theory of this, they showed that a single photon in such a thing carries exactly h bar L. So it adds to the spin angular momentum. I said you can do this addition for actually paraxial beam. Then the addition is actually rigorous. The quantity, you can just add the eigenvalues of the spin and h bar L. And of course, these are traditionally created. Now, we started, and this was the original work, and you can use, of course, with an SLM, you actually can do everything, right? But this still costs a lot, and they are slow. So one of my goals in the future, I would like to make the equivalent of an SLM using metasurfaces with some physical mechanism, not yet well determined, but I think there is no physics, there's nothing that says that it can't be done. Like an equivalent of an SLM with orders of magnitude faster speed. Can you make an SLM that has a nanosecond time scale? That would be fantastic. Even 100 nanoseconds, 10 would be great. So this is a concept of spin to orbital angular momentum converter. You come with light in a well-defined spin, left or right circular polarized, and you come out with some orbital angular momentum with a vortex beam. And in fact, people in quantum optics know that a group in actually Italy by Marucci in the 90s or late 90s using liquid crystal plate called Q plates was able to demonstrate this. But I think it's sort of that it's very hard to do, and certain things are not at all easy to do. Like if you really want to create high Ls or do more nifty stuff. So we started to look at this. And so this is now, we decided to do this stuff with our titanium dioxide fins. So this is actually how the geometric phase works, okay? This is designed a half-wave plate. So if you go through the Jones calculus, we just left circularly polarized light, you will see that you will come out with the opposite circular polarization. Now I create a phase map that has the following rule here, that the rotation of this, and there is another factor, most importantly, that I forgot, which is the so-called Berry phase. So if I look at an individual fin here, I will get a phase, I change the sign of the polarization, I get a phase factor which is the exponential of I2 alpha, where 2 alpha is the rotation angle. Okay, so now if I change the rotation angle with position by a certain rule, and I can decide any rule, if I want to make a lens, it'll be an hyperbolic phase function, and if I want to make a vortex, I want to use this kind of mapping, right? So the local rotation of the fin has to scale with the azimuthal angle. So then if you go simple math here, just simply Jones calculus, you find that there is this term here that describes an actual vortex. And in fact, the pioneering work with metallic structure was by the group of Eretz Asman at the actual Technion in the actual Midayar. So this is a metasurface that creates a vortex beam with L equal 2. Okay, and I will not spend, this is well known. If you want to determine, if you have a vortex, you not only measure the intensity with an actual camera, but you have to do an interference with the original beam. So if you have a vortex like this, the way to think about it, and I want to see the spiral, I need to interfere it with the original beam, let's say a Gaussian beam, and the equiphase point, if you look head-on at the wavefront, you'll see a spiral. And the more complex the spiral, like if you have two intertwined vortices, you will see two spirals, so the higher the orbital angular momentum, the more spirals and the dark spot at the center, exactly the center there is a phase singularity, there is a zero of intensity, will become larger and larger. So this work we did was published in Optics Express recently, and for example, we designed a metasurface that creates a vortex beam with an angular momentum of 1. Now, you can see here that the data look quite nice as you change polarization. Now, of course, here you have single spiral because it's L equal 1. This is just looking at the camera's intensity profile. These are the famous dislocations studied first, or one of the first was Michael Berry. If you now tilt the two beams at a certain angle, you see it gets very interesting. You get actually a dislocation of the electromagnetic field. If you increase the orbital angular momentum by a factor of 2, okay, you get 2 spirals, you see, you get a larger intensity. And then we say, we're really going to go for the gold here. And why don't we go really high? Now, you see, these are actually real data. And they look very, I think the data actually look quite impressive. You see multiple spiral, higher intensity. So that gets very interesting. And then we said, let's try to create a metasurface that creates a superposition of actually vortices, okay? A superposition of a field associated with L equal 10 vortex and phi. And so what you do is actually, this is what we calculated with a simulator. Basically, the agreement is quite good. There is some edge effect here due to the outer part. And when Michel Lukin saw this, he said, Federico, we need to collaborate and do some interesting quantum optics type of experiments. So I think here there are some interesting possibility to do quantum optics and so forth with this stuff. We had also found to revisit holograms, you know, and for example, we asked the question, this is addressed in this paper here below, can we design a metasurface to act as two completely different optical elements so that you encode two images completely different and you access them independently with two orthogonal polarization? Okay? That's the only mathematical requirement of orthogonal polarization. So, for example, you encode two images here. The images can be an arbitrary phase map here, and this is an arbitrary phase map. And you access it with two orthogonal elliptical polarization. It could be anything, a plus CP, right circle, left circularly polarized, and so forth, or two orthogonal linear polarization, and it can be done. The math is actually quite interesting, the whole procedure, and Balthasar in particular deserves a lot of credit who have invented this. And so here we were able, you see, to see two completely different images just with two opposite polarization, RCP. So it's an interesting, again, the metasurfaces act as any two optical elements. By the way, and we are in the process of doing, you can create a phase map that for one polarization acts like a lens. For the orthogonal polarization, elliptical, for example, it actually creates an actual image. So you can do a lot of very interesting games with this stuff, and we are quite excited. So the way it's done here by combining the propagation phase, okay, actually with the geometric phase, okay, and combined together, we can make this very interesting phase map. So this is sort of getting to the end of my talk. Our vision is that meta-lenses will have a very significant impact for technology. Look, it's not because I'm saying it. I'm just a university professor, right? But since we published our paper, we got an enormous interest from industry, which has continued unabated for more than a year. So after hearing this, it was inevitable to do this. We created a new startup called MetaLens, which Rob Devlin, my student, will join in 1 month. The other co-founder is an experienced CEO, Bart Riley, and we have raised substantial capital from investors, and have received some really major industry backing. So we are quite excited about it, and so this is the end of my talk. Thank you.